Okay, so let's move over to major concepts. We're going to talk about initial value problems, step functions. We're going to talk about procedures. We're going to lay out the procedure once again and then bring up this idea of a step function. Yeah, not too bad, I guess. Here comes the chat or the URL for the live stream. And then let me move us over to Canvas to show you some new stuff there. Right. So up on Canvas, what you'll want to see is in section D, if I click that link, which I've already done right here, then what you can find is that this morning or this afternoon I went through some old file footage, some videos, and I found some useful dialogue associated with the step function that we'll have today, and I broke out some just chunks to give you quick access to the material that we're going to talk about today and references there. And then we're going to do some heavier Laplace transforms today to find this step function, and that'll be the next phase of the course. Matt in chat is asking, can we get some more detail about the second exam? The second exam will be much like the first in terms of structure, construct, and all that. You'll be allowed 1 page of notes again, and that exam will happen on April 13th, right? And that'll be the week of E-days, and so that's a Tuesday. And then what else would I say about it? I would say that it's going to be about second order constant coefficient systems. So you're looking at root finding with homogeneous solutions, the method of undetermined coefficients, and then we will also have Laplace transforms on the exam. So there you'll have the Laplace transform sheet, and that's kind of the lay of the land. I'm not sure if that's answering your question directly, Matt, and so let me know in chat or in audio whether there's more to that. Oh, no, that's cool. Great, great. So let's get on with it and do some Laplace transforms. I figure if there are 50 of us here, then we are interested in just boogieing on with work. That's why we're here. So I'll fade out really quick. Have I told you? Yeah, I've told you about the new videos on Canvas. That's good. Coming back in. What would I tell you? Well, I will tell you that the Laplace transform trades derivatives for multiplication. Right? What does that mean? When I take the Laplace transform, I don't have any derivatives anymore, but I do have S variables lying around. Okay? And so it trades those derivatives for multiplication, and I'll also say some initial conditions, but I want to make the statement derivatives for multiplication because that's a pretty general way to think about integral transforms. And it trades calculus for algebra. A second order linear constant coefficient inhomogeneous initial value problem becomes, well, this is what it becomes in Laplace side. Okay, these green highlighted terms here, those are the initial conditions, right? So the initial conditions of the initial value problem, they end up just floating around as these numbers up in the numerator of the Laplace transform of the solution. And then down here, in the denominator of the Laplace transform, what is this thing always going to be? This is going to be the characteristic equation for the ODE. Okay, and why do I highlight that the characteristic equation is there? I want to highlight it for the following reasons. Reason one, right? What are the types of roots we could get from the characteristic equation if we get real different roots in this characteristic equation? Well, up in the numerator, we're going to have some of our initial conditions. In the bottom, we're going to have the characteristic equation. And what's happening here is we're figuring out part of the homogeneous solution. And so if the roots are real and different, then that tells me about exponential functions. And if that's telling me about exponential functions, then that's telling me about table entry number 12. Number 2, I could have repeated roots. And when I have repeated roots, I'm going to get exponential functions. But one of those exponential functions will be multiplied by a t, And so that's telling me to go and search for table entry 12 and table entry 16. In both of these cases, what is the technique that you're going to apply? Both of these cases, you're going to be looking at applying the partial fraction decomposition. Okay? And then the third possible case is that we get complex or imaginary roots. And then what are we going to find out here? We're going to find out exponentials are coming together coupled with sinusoids. What table entries am I going to look at here? That's going to be number 17 and number 18. And then what tool am I going to want to use here? You're going to encounter completing the square. So those are the three basic types that'll hack out here. And so let's highlight some of those types on the table. Number 3, whoa, that's not super great coloring there. Number 3, I'll outline in pink right here. Well, that's going to be complex exponentials and sinusoids. So you're looking at table 17, table 18. You're looking for some square completion. You could also get, maybe the exponentials aren't there, 13 and 14 coming into the mix too, I should say. Or you just figure out that A is 0, and if A is 0, 17 and 18 become 13 and 14. And then here for the real different roots, where am I going? I'm going at table number 12. And then for the complex roots, where am I headed? Or I mean the repeated roots, where am I headed? I'm headed for table entry 16 and then also table entry 12. Okay? So what's going on here is that all of this stuff that's hacking out, this is part of the homogeneous solution. Yeah, imaginary. Img. Right? So that stuff is part of the homogeneous solution. So why do I outline these three ways? Because you want to use that part of the homogeneous solution to drive where you're going on the table. Because we can look at the homogeneous solution, look at the characteristic equation, get an idea of the type of roots, and then that'll guide the process in the table. And we've gone over most of these processes. We're going to talk about repeated roots next. Well, if that's the case, what else is going on in the game? In the game, we also have this portion of the puzzle. And with this portion of the puzzle, this f of s, that's coming from the external force. And with that f of s and the external force, that's getting mixed up with this characteristic equation right here. And so what's always going to be needed at this stage is partial fractions to break up f of s from the characteristic equation. And then after the partial fractions have been used to break up the characteristic equation, what do we do next? We use table. We use the table and the ideas over here in orange that guide where in the table we're going to land, really. Okay. So that's more overview of what's going on when we're thinking about solving initial value problems with the Laplace transform and how we want to use previous concepts to guide us through that. And now what we want to do is we just want to experiment with a couple more initial value problems before I bring up this idea of the step function, which is a new function, which is really why we've built this technique out so as to handle what will be a new function here in a little bit. So in chat, it's being asked, are we going to encounter hyperbolic sine and hyperbolic cosine in our Laplace domain, or the inverse Laplace domain very much? Yeah, I want to say some words about the hyperbolic functions. They are an offshoot of the exponential function, but then again, so are sine and cosine. I don't know if I'll hit it today. If you use those transform table elements, that's totally fine if you recognize them. And apply them correctly, but they need a little bit of massaging so you have some idea of what those things are. The first thing I can tell you is that if sine and cosine parameterize circles, hyperbolic sine and hyperbolic cosine denoted with an H parameterize hyperbola. But that's not the key part of the talk. Hopefully I can talk a little more about that. They're not too crazy of a function, and it would be not bad to have that at least exposed to us these days. It used to be talked about in the calculus sequence, which is why they're here, but I think the calculus sequence got rid of them for some reason. Okay. So what I want us to do now is, with these ideas, let's practice some more. And so let's look at this problem right here, and I will put as always, the 2-minute timer up. And so with this 2-minute timer, let's work on practicing the procedure of solving this initial value problem. All right. So I've made some headway here, right? And I'm going to finish off this last step and solve for capital Y of S, right? This is the level of detail I think that should be reported out for the work. Maybe not necessarily these Laplace transforms of y double prime plus 4y prime plus 4y, or the Laplace transform of the right-hand side. You know that you're going to do those things. I leave them here for the notes so that you can see, if you're unfamiliar, feeling really uncomfortable, what that first step is. But after that, we just go into the table and we write down the Laplace transform of the second derivative, right? I wrote it down symbolically here, and then I introduced the initial conditions. You probably want to be getting to a point where you can put the initial conditions right in, but I think it's good for note-taking purposes to leave them. And then this is 4 times, there's my 4 times the Laplace transform of y prime, and then here's my 4 times the Laplace transform of y, which we write as capital Y of S. And then, let's see, I have negative s times negative 1 minus 5. And then I have a negative times a negative 1 right here, so that's a positive 1. But remember that positive 1 is being multiplied by this 4 out front, so I pick up a plus 4. And then on the right-hand side, we have the Laplace transform of 6e to the negative 2t, so that's going to be a 6 over s plus 2. And then in this parentheses quantity right here, I get s squared plus 4s plus 4, which is the characteristic equation. And so ultimately I get that y of s is equal to, okay, I take the initial condition terms, I scoot them over to the right-hand side. So that's a negative times a negative, giving me a positive s, but I move that over to the right-hand side, so I pick up a negative s. And then I have a negative 5 plus a 4, so that gives me a negative 1, but then I scoot that over to the right-hand side, so it becomes a positive 1. And then I have a plus 6 over s plus 2, right? And then since I'm solving for y of s, the last thing that I need to do is divide the whole equation through by the characteristic equation, which is going to be s plus squared plus 4s plus 4. And then in the denominator over here, I have an s squared plus 4s plus 4. Okay? So I'm going to freeze this really quick, and I'll fade out, and then I'm going to jump up to the next screen, because what I want us to notice is look at the term that has the 6 in the numerator. That 6 came from the right-hand side of the ODE, right? So that 6 is a placeholder for where my capital F of S is, and then the negative s plus 1 that's in the numerator on the first term of y of s, that comes because of the initial conditions. And so I'm going to quick jump back to the previous slide in 3, 2, 1. And there are my two terms. There's a term with initial conditions and a term with my right-hand side divided by my characteristic equation. That is how the two terms will always appear on the Laplace side. And so now we've seen that manifest in 3, 2, 1. Here's my initial condition term. And here's my capital F of S term. One thing that I should drive home here is that you do not want to combine these fractions. They're really trying to tell you about two-ish different pieces of the solution that you expect to see in the time side. And if you were to bring these fractions together, it's not going to make a lot of sense how to proceed. Okay, and that's just a general rule of thumb. So now I'm going to simplify this a little. This is going to be a negative s minus 1 all over. In this denominator, I have an s squared plus 4s plus 4, but that's really just s plus 2 quantity squared. And then I add to that 6 over, well, in the denominator, there was an s plus 2, but then this characteristic equation is s plus 2 quantity squared. So really, I have s plus 2 cubed. Okay. So what am I thinking? In green, I'm going to highlight my thinking from mass Springland. Well, I'm going to get r squared plus 4r plus 4 is equal to r plus 2 quantity squared being equal to 0. So what does that mean? That means that r is equal to negative 2, and that's a repeated root. Since it's a repeated root, what am I thinking for my homogeneous solution? That's going to be c1e to the negative 2t plus c2e to the negative 2t. But this e to the negative 2t is the same as this e to the negative 2t, so I need to make the second one linearly independent from the first. That means I pick up a t multiplier. Okay? And then my y particular of t, I would say, well, what is my right-hand side? That's e to the negative 2t, so I'm going to say e to the negative 2t, but then give it the undetermined coefficient a. But then I notice that this function is in the homogeneous solution, so it needs a t. But then I notice that once I multiply by a t to make the particular solution different, that again appears in the homogeneous solution, so it picks up a t squared. Okay? That is a blast from the muck past on how we would do this. And so, what does that do in my mind? Well, that informs where I should be looking in the table. In the table, I should be looking for exponentials because that's what's driving this problem, but I should also be looking for t multiplications on those exponentials. And that is going to be table entry number 16. Okay. So, what is this term right here? Well, it looks like table entry 16. And if that's the case, n is equal to 2. So I need to make sure there's a 2 factorial in the numerator. And then if n is equal to 2, that means out front in the time domain, I have a t squared and then an e to the at. But what's my a here? My a is negative 2. So I'm going to get t squared e to the negative 2t. So this term right here is looking a lot like my particular solution. Okay. Now, what is this term right here? If this term, the 6 over s plus 2 cubed, is my particular solution, then this term right here, that must be related to my homogeneous solution. And so, that is where I'm going to need to do my work. Oh, that's not table entry 6. That's table entry 16. All right. So, step 2. Table ready. Okay, in step 2, getting these things table ready, how am I going to think about this? I'm going to think about this first as this function here, which is y2, and then this function here, which is, or sorry, y1, in this function here, which is y2, in the Laplace side. And so what I'm going to do is I'm just going to work on these a piece at a time. I'm going to prep out y2 and I'm going to prep out y1. So the first thing I'm going to do is I'm going to look at y2 of s because it's just about ready to go. And y2 of s looks like 6 over s plus 2 quantity cubed. I look at table entry number 16, and when I look at table entry number 16, I see that n is equal to 2, and then a is equal to negative 2. So if I want this thing ready to go, this thing looks like 6 times 2 factorial, but I just can't multiply by 2 factorial in the numerator without canceling it out in the denominator. And I know I can use the 6 that's already up there to kind of make that happen, but I'll just use multiplying by the number 1 because maybe I didn't get something so nice as a 6. Maybe it was a prime number up there. And then this is s plus 2 cubed. So what does this tell me? This tells me that little y2 of t, which is the inverse Laplace transform of capital Y2 of s, is equal to, what's that, 6 divided by 2? That's a 3 times a t squared e to the negative 2t. Okay. So that's y2. I've handled that. But now what I got to do is I've got to deal with y1. And so I will freeze screen and then start handling y1 on the next page. Actually, I don't have a next page, unfortunately, because the notes are laid out in a certain way. So I'm just going to drop down a little bit into this section. Let me prep it out here. Okay, I'm going to switch over now. It won't be too abrupt. There we go. So now I'm going to work on y1. And when I work on y1, what is this going to be? I've got to use partial fraction decomposition here. I don't have to. There's a more clever way to do this, but it confuses people, so I'm not going to do it that way. And so if I see a term in the denominator and it's raised to a power like we've seen 1 over s squared, how am I going to partial fraction that? That's going to be a over s plus 2 plus b over s plus 2 quantity squared. But if I multiply these together, this is a times s plus 2 quantity squared plus b times s plus 2. And then in the denominator, I have an s plus 2 times an s plus 2 quantity squared. And whenever we use this repeated linear factor, what I'll notice is that the denominator on the right is not equal to the denominator on the left. Right? There's an extra factor of s plus 2. So what do I have to do? I have to cancel out one of these s plus 2's. And then that means that now the denominators are equal, and then the numerators say negative s, or negative quantity s minus 1 is equal to a times s plus 2 plus b. Sean, if you want to see a way of doing it without partial fractions, then just hang out for a couple seconds after class. It only works on this one case. So that's why I don't talk about it a ton. It's not super extendable. Okay, and now if I say s is equal to negative 2, then on the left-hand side I have negative 2 minus 1, which is negative 3, times another negative, that's a positive 3. And then on the right-hand side I have b. So b is equal to 3, and then if s is equal to... Well, now I don't really have another s that I can choose, but there are a lot of different ways to go about this. If s is equal to negative 2, this a term goes away, but now I could choose another value of s, and that's totally fine, or I could recognize that the constant on the left is equal to negative 1 times 1, so that's a positive 1. And then the constant on the right is 2 times a plus a b. So if b is equal to 3, then 2 times a is equal to negative 2, and so a is equal to negative 1. All right. Tons of fun. I'll leave us right here, and then I'll move this exercise down. And so now what have I found out? I found out that y1 of s is equal to negative 1 over s plus 2 plus 3 over s plus 2 quantity squared. And so what is little y1 of t? Well, that's equal to the inverse Laplace transform of capital Y1. But what is the inverse transform of negative 1 over s plus 2? We go to table entry number 12, and that gets us negative e to the negative 2t. And then what is the transform of 3 over s plus 2? Quantity squared. So this was table entry 12. This one here is table entry number 16. And what we get for that is plus 3t e to the negative 2t. So at the end of the day, what is the solution to my whole ODE, or initial value problem? That's going to be y of t, and that's going to be my previous result, which is negative e to the negative 2t plus 3t e to the negative 2t plus 3t squared e to the negative 2t. Huzzah! All right. So this section of course material is certainly called working hard and not necessarily smart. Questions about anything that was seen? That must have been a really fun problem because we lost four people along the way. Have fun in your spring break. All right.
So real quick.
Yeah, totally. A human. Yes.
So real quick, I was a little bit confused as to that little side note when you did muck and how you kind of brought that into the whole problem.
Yeah, so here, let me see if I can zoom out a little bit so that I can have both things on the screen. So here in green, I'm just kind of feeling out what would happen if I were to have done this problem through previous means, right? So here's my homogeneous solution because of the repeated root. And then here's my particular solution where I pick up 2 extra t's because the first round of particular guessing is part of the homogeneous solution, so I got to t multiply my way out, right? Well, why would I do this? Well, all of this right here is telling me about the fact that table entry number 12 about e to the at is going to get involved. And then table entry number 16, which is about t to the n, e to the at. So why I'm thinking about it with the muck mentality is because I want to know where in the table I should go searching. I don't want to just canvas the whole table. I want to go into particular table elements and start trying to use those.
All right, sweet. Thank you.
No problem. Yep. Okie dokie. So what we'll do then is we'll outline the next problem to get an idea of the partial fraction damage that's coming down the pike, right? And to be able to take a bird's eye view and see the Laplace structure, because there are only so many Laplace problems from start to finish that we can do, because they get lengthy if you're explaining them. If you're just blasting through the algebra and you're good at algebra, then they can be pretty fast, right? But talking your way through, they get a little arduous. So what I'll do is I'll move this up, and what I will set up here is, what would the Laplace transform look like? It would look like s times capital Y of s minus y of 0 plus capital Y of s is equal to the Laplace transform of cosine t. So why doesn't somebody in chat tell me what the Laplace transform of cosine of 2t is, or you can tell it in audio, and I'll just, while that's going on, I'll slip in the initial condition here. And then do a little simplification on the left-hand side. All right, so cosine of 2t is coming in on chat. That's going to be 2 over s squared plus 4. Okay. So that means that if I solve for capital Y of s right now, I'm going to move this negative 2 over to the right-hand side, so it's a positive 2, and then I divide by an s plus 1, and then there is a 2 from the cosine 2t term divided by s squared plus 4 times s plus 1. Okay. This 2 came from the initial condition. And so what function is this talking about? Well, if I look at table entry 10... Oh, yeah, good call. Yeah, S. Stop. Just an S in the numerator. Thanks. I was writing down the transform of sine. There's an S in the numerator. Shows you how little I care about the numerator at first. The denominator is really where the show is. So here's a negative 2 coming from the initial condition. Now on the right-hand side, it's a positive 2. Right? And so what is this talking about? If I go and look at table entry 12, this is talking about e to the negative t. But what is that? That is a homogeneous-like function. Okay? Because I'm looking at y prime plus y. If I got rid of this cosine 2t, what would this equation be? This equation would be y prime homogeneous is equal to negative y homogeneous. What function, if I take the derivative, gives me the negative of itself? It's e to the negative t. So this function here is talking about a negative, or 2e to the negative t. Okay, here's the point that I'm really wanting to get after here. What am I going to have to do here? I'm going to have to break this out with partial fractions, right? And what is this going to look like with partial fractions? This is going to look like an a over s plus 1 plus what over s squared plus 4. Tell me what this numerator is. Yeah, that's a bs plus c. And then once I process this with partial fraction, so here's another e to the negative t. And then this term right here, this is going to be a cosine. But remember in muck, you would guess cosines and sines in pairs. And then what's this part going to be? Well, that's going to be the sine function. So let me highlight that. This term is going to be cosine. And then this term is going to be sine. Now, we can, of course, do that, but then we're going to be in a partial fraction nightmare. But part of what I want you to think about when working initial value problems is how to see the steps coming. Somebody in chat was like, that's making a bold assumption that we're good at algebra. And I get that, right? Algebra is something that's probably pretty far away in terms of when you were practicing it super heavy, right? Because you've practiced a lot more calculus up till now. But what can really help your algebra out then is at least knowing what roughly should happen and then crying a little bit and then making that happen and then crying a little bit more and then reflecting and then being like, make more stuff happen. Okay. Okay. All right. I'm hearing this chat. They're like, yo, that sounds really technical. So, with that said, how about we break it down a skosh? How about we just drop the intensity down a little bit? Yeah, right? It's like, I can't remember how to do algebra. I just do calculus. It's like I can't remember how to do arithmetic anymore. I just use letters. All right. Oh, wait. I'm going to leave it frozen there so that I can get the next slide ready, and then we'll end off on this material, and then we'll get into spring break. And I promise that this will not be a brain break. Okay. Here we come back in 3, 2, and 1. I make a note here, see posted video. There's a posted video about this, but we're going to talk about it just the same because this is an important area to start up clean. Now, why did we start any of this stuff? We started any of this stuff so that we could get the following type of function up and running. Okay. Here we go. I've got this mass spring system, our quote-unquote mass spring system. What am I going to do? I'm going to start the experiment, and here's how I start the experiment. Start. Yeah, and it's a pretty boring experiment now, and then I'm going to say, oh, I'm going to thwack it. Okay. And then sinusoids emerge, right? That's the idea. But if I look at the whole experiment, what was going on is for the first 10 seconds, nothing was happening. And then after 10 seconds, because of an external agent, all of a sudden the system is doing something. And so what we want to do is we want to introduce some mathematical functions that are going to act like a switch. Right? And what do I mean by a switch? I want to turn behaviors on and off, and I can do it, right? Experiment starts, turn behavior on, turn behavior off. Maybe I do that a lot, right? But right now, we don't have anything that's going to act like a mathematical switch. And so let's define it. What we're about to define is called a primitive for piecewise functions. And it is called the Heaviside, after Oliver Heaviside, who used it heavily and got involved with the partial fractions because it's called the Heaviside cover-up technique. Or it's called the unit step function, and so here's the notation. I'm going to have a u. U is the function. That's the special name given to this function. And then I have a t minus a is going to be the argument of the function, and I can also write this as u subscript a of t. What is this function? This function is the number 0 whenever t is less, well, let's do the following. First, it's going to be the number 0 for t greater than or equal to 0 but less than a. Okay? And then it's going to be the number 1 for all t values that are greater than or equal to a. Okay? So this is the piecewise function, right? 0, and then all of a sudden at a seconds in time, there's a switch to the number 1, right? And it's a primitive because all I'm really messing with here is the number 0 and the number 1. Okay? So what does this look like if I were to graph this function? There is a point in time at a seconds, and that a is important. It appears both in the piecewise definition, and the call to the function itself is saying, yo, there's this thing a, and that thing is super important. Why is it super important? Well, prior to a seconds, this function is 0. So I'm going to do this. 0, 0, 0, 0, 0, 0. I'm not having the system do anything. And then after 1 second, or a seconds, the function becomes the number 1. This is the graph of the Heaviside function. And so how should I think about this? I determine some point in time where at that point in time I go from the off configuration, which is green, which is 0, to the on configuration, which is the number 1, and it's this purple section. So using this as a primitive, I can set up other sorts of step function or of piecewise functions. Okay? So this is called the unit step function, Heaviside step function. Heaviside's a name. His name was Oliver Heaviside. I don't know why, but I picture him as like a sturdy individual. Like if you've ever seen a picture of the Earl of Sandwich, that's kind of what I'm picturing in my head. Not that you should know what that is. Anyhow, it was like in a Mr. Wizard I saw like when I was a kid. But anyhow, f of t. Let's look at an example of how this might work. F of t is equal to a piecewise function. That function is going to be t from 0 seconds up until a seconds. And then it's going to be the number 0 for t seconds, or a seconds, and beyond. Excuse me. What does this function look like? This function looks like well, first I got my axes set up. This function I'll graph in green for the first a seconds. So there's this point in time at a seconds where this function changes its characteristic behavior. What was its characteristic behavior before? It looks like the line y equals x, and then at a seconds it changes. It has a change in behavior. And what is that change in behavior? I think we were switching over to purple. And then it becomes 0. So what is this function going to do? Think of a mass spring system. You got this mass spring system that wants to oscillate. You attach a rod to the mass, and then you start pushing downward with a force. That force starts off at 0, but it linearly increases up to a newtons after a seconds, and then all of a sudden you just walk away. You're like, I'm done with that. Right? So this allows me to get more complicated external forcing functions into the mix, where those external forcing functions have changes in behavior in time. So I go up, I force the system, I increase the loading, the forcing of the system up until the point where I stop, or I didn't have to stop. I could have changed to something else. Maybe you want to make a triangle here so that you're loading it and then you're unloading it, right? And now we have the ability to change these sorts of things. But you know what's pretty lame to work with? Well, piecewise functions, because what would I do if I were working an ODE? I would work the ODE for the first A seconds, and then I would work another ODE after A seconds where that force was absent, and then I'd try to like splice them together. That feels funky. Well, let's try to set this up with the unit step function. Okay. Here's my f of t. I don't want to write that piecewise nonsense anymore. So this is what I'm going to do. I'm going to write this as the function t, right? Because it kind of is the function t, right? It starts off, it looks a lot like the function t to me, right? But I don't always want it to be the function t. Eventually, I want it to be 0. And so I have this idea. I'm like, oh, I got that. Don't worry. Here we go. I don't want it to be the function t. I want it to be the function 0. There we go. But t minus t is 0, so now the function is always 0. I want it to be t for a little bit, and then I want it to be 0 for the rest of the time, and I need it to switch between those two behaviors. If I just call it this stuff right here, then it's t. But then if I call it this stuff right here, then it's 0. Right? So how am I going to do that? Well, what I'm going to do is I'm going to multiply this second t by u of t minus a. Why would I want to do that? Well, what is this function that I have written here, which is u, for all t that is less than a but greater than 0? And then what is this function u listed here for all t that are greater than a? So if t is between 0 and a, what's this unit step function? 0, right? And then all of the sudden at a seconds, this unit step function here becomes the number 1. But then when it becomes the number 1 at a seconds and only a seconds, this u becomes the number 1. It multiplies the variable t, and then I get a t minus t, which is 0. So what is all of this going to be? This is going to be, no, I guess I have it. This is really it. Let me rewrite it. T minus t, or no, let me rewrite it in the following way. This is how I would say it out loud. I need to make the function f of t. So what do? I start off time by turning the function t on. And then I'm going to subtract away because I'm going to turn the function off. What am I going to turn off? I'm going to turn off the function t. When am I going to turn off the function t? I'm going to turn off the function t at a second. So I've got to delay this second player negative t from coming into the mix until after a seconds. Okay. So this is a representation of the piecewise function using the unit step. And now if I can get the unit step involved in Laplace transforms, I'll be able to put all sorts of kooky functions on the right-hand side of my mass spring system and then get a bunch of changes in behavior. That's what we've been building up to. This is the function. We're going to do some work with this. Yeah, so these two statements right here are equivalent. You can write it as this piecewise function, which tells you a lot about what's going on, but doesn't give you a good algebra to work with. Or you could write that a primitive piecewise function, which is the unit step, so you can rewrite this piecewise function using the unit step, which gives you a nicer algebra to work with. All right. Yeah, and then Matt's asking, couldn't you just write this as t factored outside of u of t minus 0, saying, yo, start the first one up at time 0 and then turn it off at time a. And that's legit. You can totally do that too. Cool. So if you're if there were 3 parts to the piecewise function, would you multiply the 2 step functions together? We won't ever multiply step functions together. For larger piecewise functions, what we'll do is we'll turn stuff on and then turn stuff off. There will just be more terms that are added together. Cool. So I will end there for today, and I'll say have a happy spring break, enjoy yourselves, and if you are interested in this and have a little more spunk left, go and check out the videos that I have listed, and that'll get you prepped out for when we return, or go and do nothing and play Breath of the Wild for a few hours. Either way. But other than that, have a good day, enjoy your spring break. I will see you when you return.